Today we'll be covering the linked list, and it's a good one, so strap onto your seats. Before that though, if you want to catch up or have missed our previous episodes covering data structures such as the array list or the stack, click the card in the top right corner or the link in the description below. That'll take you to a playlist containing all the videos in our Introduction to Data Structure series so far. A lot of that information will be useful for today's discussion, so make sure you're up to speed. As I mentioned before, today's data structure is the linked list. We're going to start off with some basic information on the linked list, such as some background and a talk about the structure of a linked list. Then, we'll briefly cover how we create linked lists before diving into how we add and remove information from them. Finally, we'll talk about the time complexity equations for a linked list and also some common uses for them, both in computer science and the real world. The timestamps shown on your screen now correlate to when we talk about each of these topics, so feel free to skip around. But if not, let's address the elephant in the room. What exactly is a linked list? Well, to answer that, a linked list is a sequential access linear data structure in which every element is a separate object called a node, which has two parts, the data and the reference, also called the pointer, which points to the next node in the list. Wow, that is a pretty big sentence with lots of ideas within it. So let's break it down part by part. The sequential access part of that statement means that the information contained within the data structure can only be obtained through a certain method. We talked about this in our episode on the stack. During that segment, we compared them to tape measures because similarly, you can only get measurements from a tape measure through a specific method. The linear part of this statement simply means that the information or data is organized in a linear fashion in which elements are linked one after the other. Now, when we state that every element is a separate object, called a node, this means that unlike an array or an array list where every element is just, let's say, an integer, each element in a linked list will be an object which can have multiple attributes. Now, I won't dive too far into object-oriented programming right now, especially because our series on that will be starting this Saturday, but essentially, the objects, or nodes, stored within each element of our linked list will hold two separate pieces of information. These two pieces of information come together to form the node, and these nodes are what make up our linked list. Specifically, those two pieces of information are the data stored in that node and the reference or pointer to the next node in the linked list. The data is where the actual information for our element will be stored. This is where our strings or integers or Boolean values are kept. The other piece of the puzzle is the pointer. This reference points to where the next node in the linked list is stored in memory. This helps link all the nodes together in one long chain of information, kind of like a computer science conga line. So now you should be able to understand what a linked list is. Again, it's a sequential access linear data structure in which every element is a separate object called a node, in which each node contains both data and a reference to the next node in the linked list. And this cumulatively creates a string of nodes called the linked list. Feel free to re-watch this explanation if you're still confused, because it can get pretty hectic pretty fast. Alright, so the next thing I want to do is just visualize how one of these linked lists is set up. That way you can actually see what I mean when I say a linked list. So every linked list starts with what's known as the head node of the list. The head of the list simply contains some type of data and a reference to the next node. For now, let's store the integer 1, and since it's the only node so far in our linked list, the head node will simply point towards a null value, which is just to say that it's not pointing anywhere. Let's fix that by adding another node. And inside the second node, we can put the integer 2. Instantly, you can see that our head node now points to the second node instead of a null value. Also, you'll notice that now, this node, the integer 2 node, points to a null reference value, as it's the last node in the linked list. This is a pattern you'll notice as we continue adding nodes. The last node in a linked list, also known as the tail node, will always point towards a null value. This is our way of telling the computer to stop. Don't go any further because you've reached the end of our linked list. Anyways, let's now create our third node and inside store the integer 3. This node now becomes the tail node and points towards a null value, and the second node we created, the one that used to point to a null value, now points to this new node. Essentially, we're just adding nodes to the tail of the linked list and setting the reference to point towards these new nodes. And if you can understand that concept, you pretty much understand the gist of how these nodes interact. The two main takeaways from this segment are that every node has both information and a pointer, and that the last node in the linked list always points towards a null value. That's pretty much the setup for a linked list. Definitely more abstract and fluid than, say, an array or an array list would be, but dangerously powerful, as you'll see later on. Next up, I want to quickly go over how we actually define linked lists. As is the case for these more advanced data structures, we start in Java and C# by including a reference to the class we're pulling from, in this case the LinkedList class. Then, in all languages, we give a name for the linked list. In this case, I'm just calling it example LL, which stands for example linked list. Then, we set it equal to new linked list in both Java and C# with a set of less than greater than signs, with the added bonus that we have to specify the type of linked list we're creating within them. In Python, we simply set it equal to a new linked list class with a set of parentheses. Very common run-of-the-mill initializations, which is what we've really seen so far from these data structures. They're all very similar in definition, and you should start to see patterns emerging. Now we're going to talk about how we add and remove nodes from a linked list. Unfortunately for us, adding and removing elements from a linked list isn't going to be as simple as it was with, say, a stack or a queue, because of the simple fact that we can actually insert and remove elements within a linked list at any location. With a stack or a queue, we weren't able to do this because the data could only flow in and out of a few specified points. This made it so we couldn't remove an element from, say, the middle of a stack or jam an element in the center of a queue. The way that they're structured just doesn't allow for this. With a linked list, however, we can, and so today we'll be covering the methods used to add and remove nodes from a linked list, as there are actually 3 different ways to do both: adding to and removing a node from the head, the middle, and the tail of a linked list. These are all going to revolve around those pointers we talked about at the beginning of the episode, because whenever we change up a node in a linked list, we also have to change its pointer, and that can get pretty complicated. Luckily, that's why I'm here. I've set up a basic linked list here with 3 nodes we can use to play around with. Each node has a value, of course, representing the data inside the node, and also a pointer, which will point it to the next node in the linked list. The green and red coloring on the nodes with integers 1 and 3 simply indicate which node is the head node and which is the tail. Green means it's the head node, and red means it's the tail node. Now in an actual linked list, these pointers would be locations in memory, but for the purpose of this series, having it just point to the next node gets the job done. Perfect, so let's cut the chit-chat and jump right into it. The first thing we're going to be talking about is adding and removing nodes from the head of a linked list. Lucky for us, this is pretty simple. Now, to make a new node at the head of the linked list, literally all we have to do is make that node's pointer point to whatever the current head node of the linked list is. By doing this, we simply take away the title of head node from the current head and bestow it upon this new node that we're adding. It looks a little something like this. Let's take a node with the integer 0 and set its pointer to be equal to the current head node. Now, you'll see that none of the other nodes have changed in the slightest. The only thing that has changed is that this new node with integer 0 is now the head node, and it points to the old head node. Extremely simple, and the best part is that it works in reverse as well. To remove a node from the head of a linked list, all we have to do is set the head node's pointer to null. If we do this on our example linked list, you'll see that because the 0 node no longer points to the 1 node, and no node points to its location, it has been cut off from the rest of the nodes and exiled from the linked list. The old head node regains its position, and it's as if the integer 0 node never even existed. Moving on, the next thing we're going to cover is inserting or deleting a node from the middle of the linked list, and we'll start with adding a node to the middle of a linked list. Now this is probably going to be the most difficult of the 3. We need to insert the node in such a way that the pointers get readjusted accordingly without losing any of the information. Now this is going to be a 2-step process. We first make the pointer of the new node point to the node after the location we want to insert at. So if we want to insert a node with the integer 1.5 after the one with integer 1, but before the one with integer 2, what we would first do is set the new node's pointer to point to the node containing the integer 2. Then, the second step is to set the node before the location we want to insert at to point towards this new node. This would mean making the node containing the integer 1 to point towards our new node containing the integer 1.5. By adjusting the pointers of the nodes before and after the location we want to insert at, we can strategically jam this node in the correct place without modifying the entire list. As you can see now, we have a linked list of length 4, where the link has not been broken and is also still continuous. Now removing a node from the middle of a linked list is even simpler. All we have to do is make the pointer of the node previous to the one we're removing to now point to the node after the one we're removing, Then, if we delete the pointer of the node we're removing by setting it equal to a null value, we again cut the node off from the linked list and it is removed. Simple as that. So, if we now want to delete our 1.5 node from our linked list, we'd make the 1 node again point towards the 2 node instead of the 1.5 node. Then, if we delete the pointer of the 1.5 node by setting it equal to null, it gets cut off from the flow of the linked list. No changes externally to the rest of the list, just one sad, lonely node all by itself. The final type of insertion and deletion we'll be covering is inserting to and deleting from the end of a linked list. Doing this simply requires you to modify the tail element of the linked list, the one which is currently pointing towards some null value. To add a node, you just make the current tails pointer, which is currently set to null, to be pointing towards the new node you're trying to add. So if we wanted to add a node with an integer of 4, we would just make the 3 node point towards this new node. Then, by setting the 4 node to point towards null, we've made this new node the tail of the linked list, and the old tail now points to the new tail. Removing is just as simple. If we want to remove the tail, we just set the previous tail to point towards a null value instead of the current tail. Doing this on our list would require us to make the 3 node point towards null. Because no node now points to that tail node anymore, it is cut off from the linked list and essentially removed, making the old tail node the current tail node once again. So, after a bit of pointer readjustment, hopefully now you can insert and remove elements from linked lists with ease. Up next is everyone's favorite segment, time complexity equations. Now, accessing an element within a linked list is going to be O of n. Why is this? Well, just because linked lists are linear in structure doesn't mean we can get any element within it instantaneously. Linked lists are sequential access data structures, meaning the data isn't stored contiguously. Because of this, if we want to get a certain element within a linked list, we need to start at the beginning and go through every node before the one we want to find it. We do this by using the pointers as like a little map for the computer. First, go to node 1. 1's pointer gives you the location of node 2, and 2's pointer will take you to the node containing the information for the value you want. And then you can get the data stored at that node. For a linked list of size n, this could mean you have to traverse the entire thing, making its time complexity equation O of n. Searching is O of n for the same exact reason. We check a node, and if it's not the one we want, we use that node's pointer to take us to the next node and check that one. We do this for every node until we either find the one we want or get to a node which points to null, indicating we've reached the end of the linked list and the value we are searching for just isn't in it. Inserting and deleting from a linked list is a little bit complicated. Since linked lists usually only store the head and sometimes the tail's location in memory, if we want to insert or delete an element at the beginning or the end of a linked list, we can do so instantaneously using the methodology we talked about previously. However, if we want to insert a node within the linked list, things become a little more complicated. Just as we had to traverse the linked list to access or search for an element, we have to do the same thing for inserting or deleting. We must first follow the pointers till we get to the point where we want to insert or delete our node, and then and only then can we actually follow the instructions used to insert or delete a node. So depending on how or where you want to insert or delete a node at, its time complexity will be either O of n or O of 1. A little confusing, yes, but necessary to mention. So, in review, accessing, searching, and sometimes inserting and deleting are all going to be O of n, and sometimes inserting and deleting will be instantaneous. Cool. Now let's finish up by talking about some real-world applications of the linked list. Now something I haven't mentioned before, but would be remiss not to mention, is that linked lists can actually be used in the backing of other data structures. What do I mean by this? Well, we can actually use linked lists to make stacks, queues, and some other data structures we haven't talked about. This is a little above this introductory series, but it's one of the most important uses of a linked list, so I thought I'd mention it here. Because of the way it's structured, having a stack or a queue use the nodal methodology we've talked about during this episode to be the back end of its structure makes a lot of sense. If you're curious about how this works, I'll have an article linked below explaining this in better detail. I just thought it was a bit above the complexity of an introductory course. But that's not to say linked lists can't be useful in other ways. A playlist on Spotify, for instance, where each node doesn't contain just an integer or a string, but an entire song with wave data, a title, a length, etc. Then, when the track is done, it automatically points to the next song in the playlist. Another example could be a photo viewing software, where each node is an image and the pointers simply point to the next photo in the list. As you can see, while the main functionality of a linked list might be to back other data structures, it can also be used by itself and be extremely effective. And that concludes our discussion on the linked list, a sequential access linear data structure in which every element is a separate object called a node with two parts, the data and the reference, which points to the next node in the linked list. Next week, we'll cover just a small branch off of the linked list, known as the doubly linked list, and following that, we'll start getting into some of the really advanced data structures, so stay tuned. Thanks for making it to the end of the video. These videos can sometimes take quite a while to research, script out, and create visuals for, not to mention the audio recording and editing process. In total, these episodes can take up to 12 hours start to finish, so we appreciate you sticking around to the end. If you like this type of content and want it delivered to your subscription box free of charge, click the link on the right of your screen now to subscribe to the channel. As an added bonus, if you click the bell next to the subscribe button, we'll tell the Big Ups at YouTube to notify you when a new video is uploaded for no additional fee. And if you can't wait that long and are craving more of my melodic voice, you can click the playlist on the left of your screen now, which will take you to a playlist containing more programming fun. Until next time, peace.